Zoom in. So welcome everyone. We've got great speakers today. I'll give quick, super brief introductions and then ask each speaker when it's their time to actually say who you are and where you come from or whatever you want to say. So this is the Systems Performance Engineering Meetup, and today we're actually going to talk about PyTorch data loading. We're going to talk about optimizations across different GPU architectures. So we've got CUDA, we have AMD, and fortunately, I live in the Bay Area and I have access to a whole lot of folks. And actually, Eric, who is in the presenter area here, I don't think he's going to be speaking, but yeah, he and I are actually neighbors, and we bump into each other at the local Starbucks, and he got me in touch with Quentin, who will be speaking second. Chaim, I know from a few years ago. I was in London giving a talk. I actually ended up getting sick and not actually speaking, but we met out there, and I've been following his Medium posts here for quite some time. Super helpful. So I posted this link in the chat. So we're going to start off with Chaim and his partner in crime, Itzik, and they'll be talking specifically about how to optimize the PyTorch data input pipeline. So, very, very important part. And then also we'll do Quentin's talk will then come after. He'll be talking about how to write cross-architecture CUDA and ROCm kernels and potentially other platforms as well. All the links are here. There's a new GitHub repo here too, which I'll post these links in the chat here in a bit. Also, reminder that I am working on this massive book. This book started off as being only about 300 pages. It's actually up to over 500, to the point where the O'Reilly folks have asked me to kind of trim it down a little bit. The publication date here says November. It will come out this summer, way ahead of schedule, and cranking this thing out. So a lot of good tips, and I think that is it. I'll be recording this and posting it to the YouTube channel. The link to that I'll post in the chat here, but you can find it right here. So, all right, I'm Itzik. Why don't you folks grab the screen share? I'll stop sharing mine.
Okay, while Itzik is bringing that up, I'm just going to correct you, Chris. You were sick at that London meetup, but you did present.
Oh, did I?
Yes, you did. Um, and
Hopefully I didn't get
it
you
was,
sick.
no, you did not get me sick. And as I recall, it was a great presentation with handouts of your previous book.
Oh, nice.
Okay. So hi everyone. I'm really happy to be back. Today will actually be a direct continuation of the presentation I gave last month on the topic of PyTorch model performance analysis and optimization. This time we're going to focus on a very common and terribly unfortunate occurrence of performance bottlenecks in the data input, pipeline. And as we get into it, we will explain why it is so unfortunate. For those that missed the previous session, just a few words about myself. I've been working as a software developer for about 20 years and in the field of AI, machine learning, and computer vision for roughly the past 12. My specific areas of interest are in cloud-based ML and ML model performance. I enjoy blogging about the optimization work that we do. That's Itzik and I. And I have included links here to my TDS and Medium pages where you will find somewhere in the order of 70 to 80 posts on the topic of AI and ML optimization. Most of what we discuss as before can be found in more detail in my posts, and I cordially invite you to view the blog posts and reach out with any comments or questions. Let's dive right in. So the agenda, I'm going to give a brief recap of what we discussed last month and then dive right into the topic of the day. We'll talk about why bottlenecks in the pipeline are so bad, discuss some of the causes, and more importantly, how to identify them. And we will finish off with an assortment of tips, tricks, and techniques for overcoming these kinds of bottlenecks. So a brief recap. In the last talk, we spoke about the motivation for conducting performance analysis optimization, performance analysis and optimization of AI models, given the high cost of training and running AI models. ML workloads tend to be complex and are highly prone to performance bottlenecks and system underutilization. Fortunately, there are many simple techniques that can deliver significant results, some of which we discussed in our last talk. The main messages that I try to deliver is firstly the view that I feel strongly about, that all ML developers must take responsibility for the runtime performance of their workloads. And perhaps even more importantly, that you do not need to be a CUDA expert to analyze and optimize your model. We reviewed all of the many pieces of a typical training pipeline and highlighted why AI model performance optimization can be complicated. A typical training step includes many types of resources and many algorithmic components, each of which can create a performance bottleneck and result in reducing the training throughput, and also result in resource underutilization. We further discuss the holy trinity of performance optimization, where we iteratively profile the model performance to identify bottlenecks in the pipeline and also identify resource underutilization, optimize the model based on the results of the profiling analysis, and repeat continuously until we feel that we have addressed all the optimization opportunities and reached our desired maximum throughput. And we demonstrated my personal profiler of choice, the PyTorch profiler, and we demonstrated some of its different features. So that's what we did last time. In this talk, we're going to focus on the data input pipeline. So returning to our training pipeline diagram that we showed before. By the data input pipeline, we refer to all the steps involved in loading and preparing the data that is fed into the GPU, either for training, as depicted in this diagram, or for inference. More specifically, we will cover the topic of performance bottlenecks on the data input pipeline. So in a standard training scenario, the CPU and GPU have a clear division of responsibilities. The host, or the CPU, is responsible for loading data samples from disk, from NFS, or from cloud storage, pre-processing the data, collating the data into data batches, copying data batches onto the GPU. And it also does a bunch of other things, such as GPU kernel loading, logging metrics or training progress, while the GPU, the device, runs the model on the data input from the CPU, also known as the forward pass, and during training does additional activities such as backward propagation, updating the weights, gradient sharing, GPU to GPU communication, etc. In particular, the input data pipeline runs on the CPU. If one of the components of the input pipeline runs inoptimally, or contains some form of bottleneck, it may result in GPU starvation. What is GPU starvation? GPU starvation occurs when our very, very expensive GPU lies idle while it waits for data from the CPU. The situation is obviously highly undesirable given the fact that the GPU is the most expensive resource, and we would like for it to be continuously busy. We would like to make the most of it. Here is an example of how a bottleneck in the input data pipeline might appear in the PyTorch profiler trace. You can see that every 4 training steps, the training stalls on the data loading function, and the GPU utilization drops to 0. This is a clear indication that the GPU is starved for data. The reason in this case that it is stalling every 4 steps and not in every step is because in this particular experiment, we configured the data loader to run with 4 data loader workers, which means that every 4 steps, we get 4 data batches. And then on the subsequent step, we will stall while the data loaders, all 4 of them, scramble to generate more data. So this is how a GPU starvation profile trace might look. What are the common causes of GPU starvation or bottlenecks on the data input pipeline? So the most common causes are slow retrieval of the raw data from storage, CPU intensive data preprocessing, where we're making the CPU work extremely hard, sometimes overusing the actual capacity that the CPU has, compute capacity that it has. For example, in the case of training, often we will have data augmentations that will sometimes be quite heavy. And another common cause that we see quite often are bottlenecks on the host-to-device copy. We call it the last stage of the pre-processing or the data input pipeline is when the CPU copies the data batch, onto the GPU. So those are the common causes. What are the common profiling strategies? So here I group them basically into 3. One is to use PyTorch Profiler, which is as I mentioned earlier in the slide deck, is my personal profiler or profiling tool of choice. But it should be noted that in the case of the data input pipeline, using PyTorch Profiler can be somewhat complicated by the fact that we are using typically multi-worker data loader. That means that you have a lot of processes running in parallel. That makes using PyTorch Profiler a little bit more difficult. We do have a blog post where we demonstrated its use nonetheless. I included a link here for those that are interested. Essentially, what we did there was, just for the sake of profiling, we reduced the num workers to 0, essentially disabling the multi-worker data loading. And you're invited to take a look there. There are a bunch of other CPU profilers. Recall that since the data input pipeline runs on the CPU, any CPU profiler, Python CPU profiler that is available can be used, in particular ones that perhaps have better support for multiprocessing. And then there's my personal favorite profiling strategy for these kinds of issues, which is caching on the data input pipeline. This is a fairly simple technique that I personally really enjoy using, and I found that despite its simplicity, not many people take advantage of it. And that's actually what I want to talk about in the next slide or 2. So what exactly do I mean by identifying bottlenecks using data caching? So here's the strategy is summarized in this slide deck. In this single slide. So the first step is we're basically going to run our training loop with a cached data batch. Okay. The first step, we're actually going to cache the data on the GPU and iterate over the single batch, and in that way try and derive an estimate of the upper bound of the potential throughput. I'm actually going to skip ahead to the next slide for just a moment, and then we'll come back to the additional steps just to show you what it would look like in code. So I hope this is not too small for you guys to see. But if you take a look at the code on the left-hand side, what you'll see is that we're essentially pulling just a single data batch from our data loader, from the iterator. We're copying it to the device. And then we're running our training loop on that single batch over and over and over again. Now, what does this activity actually do? It basically disables the entire input data pipeline, right? In each training step, we are just running the GPU compute graph. And that gives us an upper bound on what the capacity for our model throughput is. And so that's something that I always like to do first, because that basically, I say I, but we, like I said, DeepSeek is involved in all of these activities. That always gives us a sense of what the potential is. Okay, so that's step one. Step two is, once we actually know what the upper bound is, we basically move the caching up one step in the input pipeline. So now we'll cache the data on the CPU just before we copy it onto the device. And then if we detect that our throughput has deteriorated significantly, then that'll indicate to us that our primary issue here, or at least one of our issues, is on the hosted device data copy. Okay, so just very, very briefly, I'll jump to the next slide and just show you then the right-hand side. We demonstrate exactly that situation, where we basically take a single batch from the iterator, cache that, and we'll run our training loop on that single batch. Just that this time, our training loop will include the host to device copy. Okay, I'm hoping that you guys get the general idea, because the next step is very simply continuing up the data input pipeline graph, where we basically cache at different points up the data input pipeline in order to identify at what stage the throughput drops. Okay, so we will include data caching before and after data collation, before and after augmentations, right after the raw data loading, which is basically essentially the first place on the data input pipeline that we can cache. So we find that this kind of technique provides us with a lot of information and really helps us pinpoint where on the data input pipeline our bottlenecks reside. Okay. Okay, so now that I basically shared with you our technique, I'm going to finish off with the same way that I did in the last slide deck, and the last slide that I presented in the last month, by basically just run through a bunch of simple optimization tips, tricks, and techniques, or TTTs. And again, like last time, I encourage you to refer back to my blog post for more detailed explanations and demonstrations of many of these techniques. I divided the techniques into three. One are techniques having to do with optimizing the raw data retrieval. The second group is optimizing the data pre-processing. And the third is optimizing the host to device data copy. So this is going to be, there are going to be 3 slides now. They're pretty busy. I'm going to run through them. I highly recommend that perhaps you take the time to go over them in more detail at a later point. So regarding data storage and data storage and format, so optimizing both the data storage and format, those are two separate things that can greatly impact the data loading speed. So the first one I mentioned here is to choose an instance type with appropriate network bandwidth. If you use cloud instances, usually they will come along with specifications regarding the network bandwidth that they support. And so you need to make sure that you're using one that supports what you need. You want to optimize the data storage location. Obviously, the closer that the data storage is to your device, the better. But you also want to take into account cost and flexibility. So for example, if you are training in the cloud, you may want to consider different storage opportunities that the cloud offers. On the other hand, some of them might prove to be too costly. You want to maximize the storage network out capacity. So I gave a brief example here of using S3 data partitions. If you don't use data partitions, then there's a limit to the number of API calls that you can make to S3. You might want to consider compressing your data in storage to reduce the network payload, the amount of data that's actually going across the network. Though, if you do that, you need to take into account that the decompression on the CPU might increase the CPU utilization. There are all kinds of considerations that have to do with what the file sizes, what the optimal file sizes should be, how do you want to group your samples into larger files to reduce the overhead of file retrieval. You should also aim to use optimize data retrieval utilities. We have found that the differences in data retrieval between different utilities that perform the same operation, such as Goofies versus S3FS or S5SMD versus CMD versus just the AWS command line, could deliver dramatic differences in performance. And then, of course, you have the option of tuning file retrieval configurations, such as chunk size. Regarding data processing bottlenecks, so obviously you want to tune the number of data loading workers. You don't want there to be too many so that there isn't too much thrashing. On the other hand, you do want to take the most advantage of your CPU cores. Whenever possible, you want to move data pre-processing to the data preparation phase and really only leave for the last mile only those data manipulations and data processing that you need to. In some cases, you may want to choose an instance type with a better CPU to GPU compute ratio. These vary greatly between instance types. And so if you see if your GPU is being starved, then you may want to choose a similar machine just with more CPUs in it. You should optimize the order of operators. This is a pretty trivial one, but it sometimes needs to be spelled out. So if you are cropping and then blurring rather than blurring and then cropping, could save you a bunch of CPU cycles. You should use optimized Python libraries such as JAX and Numba, just-in-time compilation utilities. Sometimes you may want to create a custom PyTorch CPU operator. I actually forgot. I wanted to drop in a link here to a blog post we wrote on this topic. I think it's optimizing PyTorch profiling and optimization. I think it's part 5, where we demonstrate how we create a custom PyTorch operator that only reads the desired crop from the file rather than loading the entire file and then cropping it, which saves us, once again, a bunch of CPU cycles. Sometimes you may want to use auxiliary CPUs. That means create a cluster in which you have your GPU and a bunch of your GPU instance type, but also a bunch of additional CPU instances. In one of our blog posts, we demonstrate doing that using Ray. Prepend some of the GPU-friendly data pre-processing to the GPU compute graph. So sometimes you may want to take one of the augmentations, such as blurring, which is GPU friendly, and actually prepend it to the data processing. I'm sorry, prepend it to the GPU compute graph. I will note that sometimes there may be other parts of the pipeline, of the data input pipeline, that might be GPU friendly, but unless it's really at the end of the data input pipeline and you're able to just prepend it to the GPU compute graph, you need to take into account the additional overhead of copying data back and forth from the CPU to GPU, which in our experience generally results in reduced performance. Um, so that's something to take into consideration. And then also you can always tune the OS level configurations relating to thread management, memory allocation, etc. And then finally, TTTs relating to the payload of the hosted device data copy. So again, a lot of these are quite obvious, but very much require calling out. So you should postpone converting int 8 to float 32 data type conversions to the GPU. You should postpone if you're using reduced precision floats, so you should cast the floats on the CPU, which will reduce the payload by half. If you have one hot vectors, and obviously you should postpone unpacking them to the last possible moment. That'll reduce the payload considerably. If you're using a lot of binary values, then you might consider using bit masks in order to compress them. You can consider using sparse data representations that PyTorch has developed over the past few years, and we have found that they're increasing in performance and utility. Try to avoid zero padding if you can. There are different techniques that allow you to avoid zero padding in the case of variable size input. And obviously, make sure that you're not copying data to the GPU that you don't actually need. We have occasionally seen people that are just copying their entire batch, even though many of the batch elements are not actually used by the GPU. So that's the last slide on TTTs. So the key takeaways essentially are the same as I had in my previous slide deck. I'm just repeating the main messages that AI ML developers must take responsibility for the runtime performance of their models. They must integrate profiling, analysis, and optimization into their development workflow. In the case in this slide deck, we spoke specifically about the technique of data caching in order to identify bottlenecks in the data input pipeline. And of course, lastly, you do not need to be a CUDA/optimization expert to boost runtime performance and reduce AI ML costs. And that was my spiel.
Excellent. Good stuff. We have a ton of questions. I'm going to just take a few, and then we want to give time to the other speaker. I have a quick question that I was just about to type, but I'll just ask it. You mentioned PyTorch Profiler, and I believe TensorBoard support is being deprecated, right? So have you looked into HTA, the holistic tracing something or other, that seems to have, it's a project that's been around in the PyTorch community for a while, that's maintained by Meta, and
So
curious.
I personally have not. Itzik, have you?
Actually, no.
So that's thank you, Chris, for bringing that up. That'll be we'll add that to our to-do list because for us, I think we actually discussed this in the last call that the fact that they have deprecated the TensorBoard support is quite frustrating for us, and we do have an action item of trying to find an alternative. So yeah, so thanks for pointing us in that direction. We'll certainly take a look, and maybe by the next time we meet, we'll have some more to share on that.
Sweet.
Just to turn the question back to you. Have you had any experience with that yet?
I'm including it in the book. I actually, so it's on the to-do list as well to migrate over, because up till now I've been using TensorBoard just like the whole rest of the PyTorch community. So and it looks like that project HTA has been around for quite some time, but it's suddenly become, top of mind for the Meta folks to get that thing working. So um, the short of it is, I think, yeah, by the next time we'll both have more information we could share. So let's keep in touch on that one.
All right, I'd love if you could just send either include a link in the
Yeah,
chat here or just send it along.
yeah. I think it's called, and I'll find it here.
Oh,
But
and just I'm seeing some of the questions in the chat. I just want to clarify that as far as I know, it's not TensorBoard that's being deprecated. It's just the PyTorch profiling support that's being deprecated. So that's an important clarification.
yeah, think of TensorBoard as the visualization side of the PyTorch profiling output, and that's what's being deprecated, right?
Right, but the other features of TensorBoard, such as the metric collections, um, there are a whole bunch of others that I actually don't use. Those are not, to my knowledge, those will continue to be supported.
Yep. Yep. Um, did you, so I think you answered some of my questions, but just curious, like at a high level, what for multi-node, data loading and even just profiling in general, yeah, how do you folks go about doing that in a larger cluster?
That's a good question. So I'm going to answer that by saying the following. It's very important. I believe that it's very important to start with the profiling and the optimization on a single node. And as a matter of fact, one of the frustrations that I have over the instance types that are provided by AWS is that a lot of the more modern GPU instances don't come in single GPU with single GPU options. And one of the reasons that I find that discouraging is because in my mind, it's very important to do the very initial design of the model, including the optimization, the profiling analysis and optimization on a single GPU instance. I think it goes a long way and saves a lot of money. So that's one thing. Regarding the multi-node, so to be honest, I do not have as much experience using PyTorch Profiler on multi-node. So I can't answer your question directly. I mean, we usually, I think that the reason that we don't is because we typically have not seen bottlenecks there. In other words, we will use it, but we can't really. I don't have anything smart to say about applying the PyTorch profiler specifically to that kind of topology.
Yeah, HTA, that's supposedly one of HTA's strengths. So yeah, distributed training workloads. Okay. And let me see, let me look for some, any Kubernetes tips from the field? Yeah, do you folks use Kubernetes?
Yes, we do use Kubernetes. But that's kind of out of left field, no?
In terms of, I guess, data
Okay,
loading, anything.
okay. So actually, Chris, when we first met, you asked me about Kubernetes. This was
Oh, that's
years
right.
ago. Do you
Yeah.
remember that conversation?
Yep, yep, yep.
So so I think that Kubernetes is a great tool. if applied in the right scenario, in the right situation. I'm I I I'm gonna pass.
Yeah, that's right.
I
Because
think
I
that
had,
I think that there's situations where it's used incorrectly, and it's very unfortunate because Kubernetes includes a lot of overhead, including a lot of technical skill. And sometimes, in many situations, it just really is not required, right? If you know what instance type you want, you know how long you're going to need it for, then allocating it using Kubernetes may be unnecessary. On the other hand, obviously, there are a lot of situations where Kubernetes is helpful. We actually have a blog post where we demonstrate how Kubernetes can be used in order to prioritize workload scheduling and make sure that if you have a lot of different training jobs with different priorities, how you can use vanilla Kubernetes, because I know that there are a lot of more advanced tools built on top of Kubernetes that offer these features. But we demonstrate how you can use just the basic Kubernetes features in order to create a priority scheduler, which is very important in the era of GPU scarcity. So I think that Kubernetes is great, but I just think that it's important to make sure that you're applying it in the right situations and in the right manners.
gotcha. One more, I think, quick question here. Where'd it go? Oh, yeah, which tools? So you mentioned the S5 command and like a
Yeah,
couple other.
yeah.
Are there other ones that have popped up recently? Because I know those have been around for a while. I feel like there's a newer one that came out.
Well, there's well, okay, so they're different. So you can group the different tools for reading data from the cloud into different categories. So you have the fuse-based solutions, such as S3FS, such as Goofy's, which has been around for a while, and such as Mount Point, which is a more recent one that AWS supports, even though it's supposedly supposed to work on other cloud storage offerings as well. And then you have the ones that will explicitly download the object files, such as S5 CMD, the AWS utility, command line utility. I don't I don't recall offhand any new ones in particular. The newest one that I recall analyzing was Mount Point, which is from the Fuse-based family. I don't know if there are any others similar to S5 CMD. Maybe Itzik, you have something to add on that topic. But we love S5 CMD.
Okay. Yeah, and the best practice there, I remember like digging deep into this at some point, was make sure that you're using like something that is like launching multiple threads, pulling from S3. It's very easy, for example, to use some like a high level like Python library that's single threaded, that's not actually taking
Right,
advantage of the
right.
parallelization
But
that S3 offers. Yep.
right, but it's tricky, right? Because a lot of these libraries will have these defaults, which in many cases will be optimal, but not always.
That's right. That's right. That's right. Oh, okay. I think we probably got to move on. Someone asked about like, do you folks use anything like Redis as part of the pipeline or any other kind of system.
I don't know if they're asking because of the shirt I'm wearing. I don't have any experience with Redis, personally.
Yeah, there's layers. So, for
Oh, rclone,
example,
yes, I see some rclone. Itzig just brought up rclone, which is also something that we have found very useful. Uh, I'll just note. Oh, and Itzig actually mentioned it here. One of the things that we love about rclone is that it really helps with copying between data storage solutions, right? So one of the limitations to S5CMD, at least the last time that we analyzed it, is that it would allow you to download from the cloud to your local file storage system. But if you wanted to manage your data in multiple file storage locations, then you would have to do it in two steps, or in two commands, whereas rclone allows you to do it in directly.
gotcha. This is a pretty active project too. Yeah, this looks great. And I think you kind of touched on one of my other questions. In the AWS world, for example, there's the FSX for Lustre, which is basically doing something like that, right? Where it sits on top of S3 and it's caching. It could be
Right.
similar to like a Redis cache, but yeah, I mean, do you folks use that or any other kind of?
So that's a good question. So we did play around with that. There are two things, and I'm not going to say that it's a not a good solution. I think that in many situations it is a good solution, but there are two there were two determining factors for us. One was cost, and another one. And it's to keep me honest here. I don't recall the details, but another one had to do with the limitations that it imposed on the number of devices, training devices or instances we're actually able to use. But I'm a little fuzzy in the details.
Yeah, there's some trickery there. And also you have to size FSX in
Right,
such a way to
right.
get the
And you
highest
also
throughput. Mhm.
have the warm start, which was really annoying if you have a really large data set. That the warm start could be very disruptive. Yeah,
That's
so
right. Yeah.
there were a bunch of considerations, but I don't want to. I think that AWS has a bunch of features, and you know, I think it's it's not. Wouldn't be unsafe to say that every feature does have a use case for which it's you know really appropriate. So I do think that I would not rule out FSX for automatic.
Last. Yeah, I mean, my experience, I actually didn't see it used as much as I thought I would have. The folks that I was working with, which were very, they were like training on, very large data sets, were just optimizing S3 and, using aspect. One very last question, GPU direct storage by the NVIDIA folks. Have you
No,
looked into that
have
at all?
not had, no.
That's one trend I noticed at this year's GTC back in March. Jensen, even during the keynote, was talking about how storage is like the next, big frontier for that company. They've kind of like tackled networking, and now they're, like really getting into the high
Right,
speed like GPU native storage. So
right.
yeah, something to
And
keep an eye.
that's limited to only the very latest GPU offerings, right? So we haven't had the privilege to use those yet.
Okay. I'm it's a yeah, thank you so much for your work, and thanks for, sharing your work as well too. It's really, really hard to find folks that are, that spend the extra time to talk about this stuff. The space is just absolutely massive. And your contributions really help folks move forward. So thanks so much.
I really appreciate that. Thank you, Chris.
And you'll be back next month, I hope. So I'll be in touch with you probably the
Okay.
night before, like I did this time. But yeah, be prepared. Mark your calendar. Yeah, I'll
All
mark
right.
it for you, actually. So,
Okay. Take care.
all right, folks. Quentin, you're up next. We'll probably go late if because I imagine you want to talk more than for 15 minutes. We will continue to record as long as you're willing to keep talking. So
All
go
right,
ahead.
great. Great. 1 sec, let me bring up my slides.
Yeah, don't forget to talk about Zyphra, to say what you
Yes.
folks do and your role, and would love to hear more.
That will be my initial spiel, yeah. Let's see here. Okay, cool. So am I sharing my screen okay? The right screen, everything?
All good.
Okay, cool. So I'm Quentin Anthony. I'm from Zyphra. That's who I'm representing. The thing I'm going to be talking about first is cross-architectural considerations. So like you have a model and some set of kernels that are running well on, say, NVIDIA GPUs is commonly what people find, and you want to run this on AMD GPUs or Intel GPUs or Gaudi or a Cerebras system or something like that. Why do I even care about this problem myself? So that leads me to Zyphra and what Zyphra is. So Zyphra is an AI startup out of the Bay, and we're trying to make personalized AI. So that's running offline, locally private on your device that is also personal to you. So sort of your model weights that learn how you like to talk to it and what your favorite things are, like sort of a useful AI agent and assistant. And that sort of introduces a very hard engineering problem, which is that I trained some model on some hardware, but then I needed to run efficiently on a Samsung phone and an iPhone. I needed to run on an Intel AI PC. I needed to run in the cloud because there's these spectrum of models on the spectrum of compute. I have Zyphra has trained much larger models that run in the cloud that are for more powerful requests if someone's asking about math or code or something like that. And then I have smaller, more agile models that are more for on your phone. And all of these models need to run efficiently sort of everywhere. And how do I do that is um, kind of the question of the talk, right? So how do I do these very low level systems optimizations so that these models run efficiently everywhere? On the plus side, the hardware is pretty much converged thanks to people like Eric. So like there are Apple neural engines on phones. On the Intel AI PC, there's a GPU and an NPU. Pretty much all hardware now has a SIMD chip on it, so that we can sort of assume GPU-like properties to optimize for. I'll also say, lastly, that we wrote an AMD kernel blog here. Let me get my pointer. One moment. Here. So I encourage you to read up on the work that we've done. So I'm not just talking about, I've actually been working on this field for a bit. And then if you want to learn more about Zyphra, this is our homepage. But with all of that in mind, let's get started. So the state of SIMD architectures, what sort of GPUs are out there, and what is the state of the field? What is everyone doing? So NVIDIA still tends to dominate in training, but AMD is catching up, is the gist. So AMD MI300X cloud GPUs are a lot cheaper. They have more VRAM quantity and bandwidth than H100. So you have a lot more VRAM to store your model. You're able to access that VRAM much faster. These two together, as well as cost, makes MI300X GPUs great for inference. So, let me get rid of this. Yeah, okay. So you have lower dollars per token. A lot less parallelism is needed because parallelism for models are always sort of a necessary evil. The communication cost is always eating into your speed, and you can tolerate much higher batch sizes, which translates to more users at once on the same GPU. You also have much faster decode because decode is memory bandwidth bound. And all of these together means that a lot of companies are sort of doing this. They train on NVIDIA and then they inference on AMD. So a lot of companies fall into this bucket. For example, Meta does all of their Llama inference on AMD GPUs. xAI does a lot of their inference. I think companies like Microsoft are starting to move these sort of things. Navigating AMD software is hard, and forward pass kernels are a bit easier to write. So forward pass is all that's needed during inference, and then during training, you need both the forward and the backward pass. So writing the forward pass kernel is a bit easier. So people have it sort of solidifies this inference on AMD regime, which I discussed about earlier. And because of these 1 through 3, a lot of these companies are doing, NVIDIA and then AMD. We at Zyphra want to reduce our cost for training as well. So a lot of the kernel work that I'll be talking about is in the context of writing better backward kernels for training, because we want to also lower our training cost. So GPU software is really hard to navigate, and optimizations cost a lot of labor and time. So therefore, we want to reuse the existing algorithms, the existing kernels, and everything else. For example, basic gem kernels, generalized matrix multiplications is what this stands for. Flash attention for the attention operation, etc. We have these very optimized NVIDIA kernels, and we don't want to spend a lot of money on a lot of labor to port them from the ground up unless we absolutely have to. So I'll be talking a bit about like how to translate your kernels and so on. What about new kernels? So what if I have something like MLA from DeepSeek, this multi-head latent attention? How can we write them in this new bifurcated ecosystem in mind? So how do I write in CUDA and then port to HIP? HIP is AMD's basically version of CUDA. Do I just write in Triton? Because Triton is a generalized language that compiles down to GPU assembly code for NVIDIA and AMD and so on. Or at least that's what they advertise. Can I do that? And so on. So this talk sort of seeks to give a practitioner's guide to optimizing kernels across architectures. I'll be pretty high level, and then we'll go into any questions people have. And then at the end, I'll talk a bit about like how does one train a model so that it's like amenable sizes for all these different GPUs are baked in. So lots of intro. Let's get into the actual work here. So some things translate when you have a kernel, let's say on NVIDIA, and you want to translate it to some other GPU architecture. So let's use flash attention as an example GPU operation that we run on an H100, and we want to run it on, say, an MI300X. We're one of these companies that does training on NVIDIA and inference on AMD. So algorithms and their structure, such as for flash attention, those will translate to any SIMD architecture. So doing an IO-aware algorithm from the ground up and flash attention, that IO awareness will apply whether you're on an AMD GPU or a Microsoft SIMD chip or Meta's chip or so on. If it's SIMD and you have these algorithmic improvements, that will apply wherever, which makes sense. Like IO-aware chunking, all of these SIMD architectures have a memory hierarchy that when you squint at them, they look pretty much the same. So they all have high bandwidth memory for VRAM and then shared memory down at the streaming multiprocessor level, and then some registers. So some things don't, and the things that don't are what I care more about in this talk. Some things don't translate from NVIDIA to AMD to Microsoft and so on. And so these are tuning, so manual tunings of what is your block size, or what is the number of kernel pipeline stages? How many kernels do you run at once? These sort of things are all sort of parameters in your kernel launch that you need to decide, and those need to be tuned per architecture. On the plus side, it's not hard to change these numbers to whatever fits your GPU. On the minus side, it definitely needs to be done per SIMD chip. The much harder thing is what I'm calling kernel flow. I didn't find a good definition before this talk. It's much harder to define, but GPU kernels, they require a lot of different hardware units. So they require CUDA cores and tensor cores for computation. They have all these memory stages like the registers, SRAM, HBM, and so on, and all of their buses. They all have different memory bandwidths. We have different like L1 caches, caching systems that we need to worry about, and their control flow instructions, such as synchronization points, overlap of different operations and such, all need to work together. So maybe let me step back for a bit as an example of like when people wrote the flash attention kernel, when Treedow wrote it, he made implicit assumptions about NVIDIA A100 chips. He made assumptions on their register size, on their shared memory size, and so on, and their bandwidths is one example. When you port this over to AMD, not only do you have to tune for this new system, but you need to rewrite the assumptions, like maybe now different tensors can fit in registers and so on. And if you just naively tune those like raw numbers of block size and so on, you lose these implicit assumptions, and you end up playing like this game of bottleneck whack-a-mole, where now your bottleneck is in memory bandwidth, and then your bottleneck is back into compute, and then it's on the L1 cache is thrashing, and so on. So these kernel flow ones are hard to find. They're also the hardest to fix, and they require you to do sort of hardware informed kernel design or redesign in some cases, which I will talk about in a bit. Needs kernel restructuring. And then what do you write your kernels in, and which ones do you can translate? That leads me to the next slide here. And I'll ground this all in code very shortly. I know this is a lot of information. It's very high level, but stick with me for a little longer. If you have an NVIDIA kernel written in Triton, then you don't need to do any translation at all. That NVIDIA kernel in Triton will run on an AMD GPU. The problem is that the AMD compiler target needs work. So for example, people have lots of patchwork to fix all of these edge cases on the NVIDIA GPU compiler. To be specific, we're compiling from Triton code, a Triton kernel, all the way down to NVIDIA, basically GPU assembly. So PTX for NVIDIA and AMD GCN on the AMD side. So very down to machine code here. Triton will give you mid-level performance, so it's really good for rapid prototyping. I can get something that was in pure Python, CPU bound, everything, to a decent GPU kernel very quickly in Triton, which is great for, and if that's all I need, then that's fine. The problem is that if I'm trying to write something more optimal, not only do I need to understand the low-level GPU programming sort of basics, I also need to understand the Triton compiler itself. And if I need to make some new optimization, that optimization needs to apply to my special case and then also not break the compiler for everyone else. I'll show you an example on the next slide. If I have a kernel in CUDA, it's a bit probably the most flexible programming model that NVIDIA provides. It also requires the most work on my own, so I kind of have to rebuild everything from scratch each time. It's definitely something I can can become the most optimal because I have so much control, but it's going to take me a lot of time to do that. Then ROCm on the AMD side gives us HIPification tool, which lets me translate a CUDA kernel into HIP. It's very easy conversion. It's basically just a big lookup table where I go from the CUDA API call for the specific instruction onto the HIP API call for this specific instruction. Big lookup table, changes all the linking so that you can build this with the HIP compiler and so on. Day one, I can get it to actually run. The problem is that while I can get it running in a day, it'll be horrible performance because it's this kernel has been completely built from the ground up in assuming NVIDIA, and it requires me to do tuning. So remember I talked earlier about just changing values of block sizes and number of kernels running at the same time, just changing values and trying to find the best combination. That's not too bad, so I have to tune. But often at this stage, I have to do restructuring. So Triton is nice in that it tends to it tries to compile down to something efficient. But if we're just doing a big lookup table, there's no thought of efficiency at all. And this all of the explicit or implicit assumptions of NVIDIA GPUs are still there, even though they're called by the HIP API. The good news is that if I go through all of this restructuring and tuning and everything else, I can get very high level performance, much better than Triton in most cases. But that's at the cost of developer time. And then lastly, I just want to talk a little bit about Cutlass and composable kernels. So these are like totally separate, no easy conversion at all. So you have to manually convert these kernels from the ground up to and from. After all the tuning, restructuring, and building from the ground up, this is probably the easiest to get high performance. I keep promising I'm going to actually show you code. Let me actually show you code of what I'm talking about. So first, I'm going to talk a bit about this Triton thing. So I talked about Triton. Let me make this a little bigger. So this is the Triton kernel for flash attention on the flash attention GitHub. So let me just show you that. So here you can go to this GitHub. You can see all the kernel code that I'm talking about. This is by TreeDAO. It's very good stuff. It's very clean. It's great for like learning kernels. But there is a Triton implementation, flash attention, that he provided. And if we see in this, so all of this will run on AMD day one. I can run the exact same code, change nothing but my build, and run this on an AMD MI300X GPU. And I'll also get all of the core logic of flash attention. So for those unaware, the gist of flash attention is that you sort of decompose. Actually, let me get up a little figure. That one might make this a little easier. So I'm going to keep talking about Flash. This is what it is. The gist of Flash is that you break down your attention operation into little chunks, And then each of those chunks is sort of a fused sub-operation of attention that doesn't require accessing this global memory, this HBM, because every time you're accessing HBM, those cores are just sitting for what feels like years for them. You want to reduce the number of HBM accesses to as few as possible. And that's what flash attention does by decomposing into these small blocks of K and V and Q and so on. And this is the core loop, the inner loop of flash attention. And this will run day one on AMD MI300X. The problem is, while this algorithmic structure is able to port over, you'll still have the lower number of HBM accesses compared to vanilla attention and so on. You will still get bad performance. And the question is, or at least at the time I ran this, and the reason why is that these implicit assumptions that I keep talking about. So the Triton compiler does not know. Actually, let me get my page marker up here. Okay. It doesn't know that in AMD world, we have a lot more SMs. So that like the number of SMs is much higher compared to H100. The amount of SRAM per SM is lower compared to H100s, and then the register file per SM is much larger. So because of this, you can store the Q tensor out of QKV and attention entirely within registers. And I was able to figure this out when I was trying to write this Triton kernel for Zyphra for our flash attention. But then I have the problem of how do I actually fix this? Since Triton is all high level, like there's a lot of loads and stores here, but none of them at the granularity of SRAM or registers. That's the sort of the magic of Triton, is that I don't have to worry about all of those low level implementation details of CUDA or PTX or assembly code for GPUs or whatever else. But I also can't fix it. I can't optimize my kernel so that I only put the Q tensor in registers so that I can stay there the entire inner loop here. So I don't have to completely, because what I was seeing is that there's like register pressure that's very high on AMD MI300X from profiling. And I want to fix that by keeping Q in the registers. What you end up having to do is you have to go within Triton and completely change the compiler, or at least make enough modifications that it accounts for this edge case without breaking everything else. And that's kind of what I'm trying to say on this slide here, is that the AMD compiler target, it needs work. So on the NVIDIA side, they've accounted for these specific fine-grained issues, and this doesn't need to happen. Whereas on AMD, I kind of have to root them out myself and find out where they are, and then also understand the Triton compiler enough to make this change. So that's Triton. That's sort of the state of Triton and the pros and cons of working with it. There's also CUDA and HIP. So this one's a bit less dense than the last one I gave. But I just wanted to briefly touch on like HIPification. I talked earlier about it's like a big lookup table. This is just more of that gist. So it changes all of the compiler linking, everything else, as well as the actual API calls within the kernel itself to just be AMD based. So CUDA free is now HIP free, and so on. CUDA malloc managed is now HIP malloc managed, and then we change all of the linkings and headers so that this compiles well on AMD. And as you can imagine, like yeah, this builds right away on AMD. But the problem is that there's no compilation going on. There's no thought of efficiency. It's just day one, it can run. It will just not run well. So that's HIP and HIPification at the high level. I don't have examples for that one, but I think the concept itself is simple enough to hand wave. So porting kernel summary. So just this first part here is that Triton is great for rapid prototyping on AMD and NVIDIA. I can take like a CPU op and make it a decently efficient kernel very quickly, same day. You're limited though by the compiler. So getting to near optimal on NVIDIA is much more achievable, but the AMD compiler target still has some holes. There's still some, for example, like the assumption about register size on AMD thing, that edge case has not been accounted for. So I have to do that myself or wait for Triton to fix this this little hole, this loophole. Convenience languages in general, like Triton, are sort of a double-edged sword. So low-level optimization becomes doubly hard. If it works, and it's great. You don't have to touch it. But if there's an optimization that needs to be done, it's always going to be harder than if I were to just have my lower level language and I could directly do the thing I need to do. So like with CUDA, HIP, or PTX, AMD, GCN, these low level programming models and assembly languages, you just need to understand the hardware optimization. I just needed to come to the conclusion, for example, with my register optimization, that I need to keep Q in registers, and I'm done. I just implement it quickly in these lower level languages, and that's it. But with Triton, I both need to understand that I need to keep Q in registers, and I also need to understand the Triton compiler enough to change it so that it can handle this edge case of keeping Q in registers. And that's an added complication. So optimization can sometimes take longer, actually, if it's handling with if it touches the compiler in any way. Yeah, so I spoke a bit on this example. I don't need to belabor it again. I think people can ask questions afterwards if they need to know about this queue optimization. Okay, then on CUDA and HIP, so general purpose GPU programming models is what these are. They're great for max expressivity and therefore optimization. HIPification lets you have something running day one, but optimization takes much more time. There's no hand holding like there was in Triton to try and get something somewhat optimal. It's all on you. In the best case for simpler kernels, you just manually tune, and then you play bottleneck whack-a-mole until optimal. Like I was saying earlier, the bottleneck is in maybe register pressure. So you fix that one, and then it's in the L1 cache thrashing, and you fix that one, and so on. And eventually you'll get something that is tuned for whatever hardware you're trying to optimize for. In the worst case, one needs to fully rewrite around the target hardware's implicit assumptions. This is exactly what I had to do for the Zyphra blog on flash attention. So if you're interested in what that looks like, please read the blog. But all of those implicit assumptions were just so baked into the CUDA kernel for flash attention, I had to work from scratch for ROCm for AMD. And then there's cutless and composable kernels. So I talked about these a little bit earlier, but I kind of glazed over them. These are optimized building blocks for common deep learning subroutines. So instead of in CUDA, I would have to like write a gem kernel or like find something else like some cuBLAS kernel to plug in. Instead, cutless gives me these extremely optimal gem kernels. They have very all these building blocks that I can just sort of fuse together into the kernel that I want to write. And they try to make those building blocks representative of as many DL operations as they can. Composable kernel is AMD's flavor of this, and I kind of am seeing a lot of people move to these two, just because it's still written in CUDA or HIP or so on, but it gives you a starting point so that I don't have to write everything from scratch. It's more flexible and easier to optimize than Triton, well, okay, so yeah, more flexibility and then I have more control, but it's much faster prototyping compared to raw CUDA or HIP. So if I were to go back, for example, to flash attention here, I can see that they check out Cutless, and that's what they use for the flash attention backend in some cases. And then AMD has their own composable kernel version. So Cutless and composable kernel and all these building block libraries are where a lot of people are moving. Let's see. Even with all of this in mind, so I can make really fast kernels, but if modern models are not trained with that diverse hardware in mind, then I can only get so far. And that leads me to the second part of this talk. So SIMD architectures are highly sensitive to their kernel input sizing. What is the size of the model? So we at Zyphra, we're training our models from scratch, as well as trying to inference them. And we have to answer the question at the training side is, how do we make this model amenable to all of these inference edge cases? Like, how do we bake in good sizes that fit on AMD and NVIDIA and so on? Because we know that we're going to have to run it on all those eventually. Why not do it from the start? And this is how to do that. I'll just go over this rather briefly because I'm running low on time. So people may have seen this Karpathy tweet where Nano GPT speed up, and the largest one being just because they rounded their vocab size to the nearest multiple of 64. Why did this happen is sort of the motivation for why I started this work. So consider 2 to the 10 versus like 2 to the 10 minus 1 neurons in a hidden layer. So just your hidden size of your model. It's the same model accuracy. It's just one neuron going away. So the model itself is not going to really be any different quality, but you can get like a 10 to 40% increase in per layer throughput of your model. Why is this? Finding efficient sizes is especially important since model designers tend to copy each other. So after the GPT-3 paper came out, everyone, people from Cerebrus and Together AI and Eleuther AI and so on, all were trying, and Meta as well, we're all copying this GPT-3 model. But the GPT-3 model had bad sizes for GPUs baked into it. So then with like very small, these are all 2.7B models, but with small roundings here and there, you can increase your throughput significantly. So for example, we get like 165 teraflops, whereas GPT-3, the original paper, got more like 120, and in some worst cases, you can get like 108, 83. Same model, same model total size, but just small roundings here and there. Why does this happen? So we just treat transformer models as a sequence of GPU kernels. So you take a transformer model, for example. Excuse me, your attention block sort of boils down to this QKV transform, and then attention score, and then attention over values, and these are just gems. These are generalized matrix multiplication kernels of the sizes that we list here. So we boil down models to their component kernels, like what are the exact GPU operations that need to happen, and then which ones take up the most time. So I'll let this sit for a second. The gist here is that any transformer model, most of its time is spent in the attention operation and the multi-layer perceptrons. So every layer is attention MLP, attention MLP, and so on. That takes up the vast majority of the total latency. And as you scale, everything else sort of fizzles away, and you're just left with these MLPs here, and then the attention block here. So let's take a look at those. What are their sizing uh, uh, sensitivities, and what should we set them to? The good news is that MLP gems just depend on the hidden dimension and 4 times the hidden dimension for this example. Things have changed a bit since then, but it's still much more straightforward to optimize MLPs. It's really just a roofline model. So as long as your hidden dimension is large enough, you can saturate the GPU and you'll get pretty much peak throughput on this specific GPU. And this holds across architectures. So both for A100s and V100s, you really just need to make the MLPs big enough and you'll be fine. That's the gist there. Attention is much more cursed. So attention at the time of writing this is that you have these sort of 3 different peaks, and these all translate to how well you're using tensor cores or matrix cores. So these are very low-level hardware units on NVIDIA and AMD GPUs respectively that are able to run matrix multiplications really fast, but they assume that they are specific sizes. And that's what gives you these different peaks. So these are all different sizes of the attention block, and just showing you get much lower throughput if the size is bad. If the size is not amenable to those tensor cores, then you have to use CUDA cores. And then it's mid-range if you're using, if your size is a bit usable by tensor cores, but not totally. The tensor cores can't divide the attention block very much. And then you can also get these very peak throughput numbers. And at Zyphra, we have these like lookup tables across all of different hardwares of all different sizes, and we're trying to find what is the peak on every single one of those GPUs. Like, what do they all have in common? And then we want to train with that exact peak. That is the gist of hardware sizing when you train. You try to train a model that will be that has amenable sizing properties on every single inference chip that you want to target. I'll talk a little bit more here. So like, for example, I talked previously about there's multiple operations that go into attention. The attention over value specifically kernel is very sensitive to something called wave quantization. That's why we have these waves that go up and down. We want to be at the very peak of this wave. So not only on the previous slide do we want to be at the peak of this attention key query score. So remember, there's multiple kernels. We also want the attention over values kernel to be at its peak. So this big matching problem is kind of what training a model looks like. And then I think I'll just explain wave quantization and then call it here. So the gist is that we want to ensure the hidden dimension over the number of attention heads has as many factors of 2 as possible. That's what gives us this peak here. It's what gives us peaks on the previous slide. That's sort of the gist. But what are these waves? GPUs are composed of streaming multiprocessors. Maybe I should have put this at the beginning, right? So a lot of different SMs. You can sort of think of these SMs intuitively as like a different CPU core. SMs contain warps or thread blocks, and warps contain cores, and those cores are either tensor cores or CUDA cores. SMs run in parallel, so GPUs are all SIMD chips, so they're trying to do single instruction but multiple data, and you have different data batches on each one of these SMs running in parallel. We want to keep all the cores busy, so we want occupancy to be as high as possible. We want all these SMs to be doing something at every single time step. So if we want to fill each SM with enough warps to hide instruction latency, and then fill all of the SMs with enough warps to keep the cores busy. Okay, what is wave quantization? So why was I seeing those waves earlier that were going up and down? So imagine I have just a single unit of work, and it fills one SM. Each unit of work fills an SM totally. So I just have a single time step, I have a single unit of work, and my throughput is just one. So let's say one T-flop. Now let's say I increase the problem size so that I have 2 units of work, so I can put them the same instruction on 2 separate SMs, use separate data, so my throughput doubles just by increasing the number of units of work. And I can do it in the same time step as well. So I can keep doing that until I fill all of the SMs. So now my throughput is at peak. All of the SMs are totally full. This would be the very crest of one of those waves, the very top. But now, let's say I have an extra unit of work, a 7th one. The problem here is that now I have to have 2 time steps. So in the first one, they're all filled with the first 6 units of work. And then the second time step, only one of them is filled. So the total throughput is 6. The occupancy is 6 in the first one, the first time step, and just 1 in the second time step. So my average throughput goes down to 3.5. So that's why we have the wave. First, we're filling with more units of work. And remember that plot was on more hidden dimensions. So as you have more neurons in your hidden layers, you'll have more units of work, and therefore you'll have this wave. So then if I have 8 units of work, then my second time step has 2, and we're kind of do this again. So we do this over and over until the wave eventually converges to very small fluctuations. That's wave quantization, and that is why it happens in that kernel. So the reason I'm even talking about wave quantization, to go back to this, is I want people to know that you need to understand what kernels your model is made of, and you need to understand the properties of those kernels. So very low level GPU understanding is necessary in order to plan your models ahead, in order to optimize them and know what daemons are hiding in the existing model that someone else trained. It's very necessary to understand what kernels are being used and what those kernel sizing properties are. For example, at Zyphra, we're rounding our sequence lengths during training and inference up to the nearest number of streaming multiprocessors on the specific GPU to lessen this effect of wave quantization itself. We're sort of padding our units of work always to the nearest crest of the wave, and this gives us edges. This gives us an edge over our competitors because we did the hard work and looked down in depth at what the GPU is doing. The last thing for the model architecture people, if you want to know what to train and what works well, we found sort of these final suggestions for you. I won't go into much depth on them. Read the paper if you care. But the gist, again, as I'll bring back, is understand your models, understand your kernels, and then understand the GPU architecture that they're running on. And that's all I have. So whatever questions people have, I am happy to answer them. I cannot see the Zoom chat, so Chris, can you help me out?
Yeah, for sure. Okay, well, I was just typing a question here for you. Yeah, there's tons of questions. First of all, on this slide, what is considered a large microbatch size, roughly?
This depends on your GPU, but as large as possible, as large as can fit is what I would say. Larger than 1. So typical values, if you just want the raw values that I tend to see, on an H100 with a decent size 7B model, I want this to be at least 4. In better cases, more 12 to 16 or something like that. Higher is better. Higher gives me more units of work, so I'm farther ahead on that wave if I ever have one.
Got it. Okay, which profiling tools do you use on a daily basis?
The Torch profiler is what I use for high level. Where is my time even being spent? Which kernel? if there's some like kernel taking a ton of time, I'll very quickly see it in the Torch profiler, and it's much more interpretable. And then I can see, okay, it came from this exact block of my model. But when I'm actually doing, like, remember I talked about register pressure and all that kind of stuff, that's coming from the low level NVIDIA Insight or ROCprof on AMD side. Those low level GPU profilers are what I use once I determine where the bottleneck lies. So let's say the PyTorch profiler says attention is taking twice as long as you expect. And then I say, okay, I run the attention block itself, and I use the Insight profiler to like look at every single tiny detail, every single like L1 cache utilization and all this kind of stuff, and thrashing. I go into much lower detail once I narrow down where it is.
How do you overlay those two? The right, like the output from the PyTorch profiler with Insight. Do you just do it manually?
I unfortunately have to do it manually right now.
Yeah.
I wish I didn't have to, but yeah.
Yeah, I think I was chatting with some of the NVIDIA folks at GTC. At least on the NVIDIA side, it sounds like that's high on their priority list to fix. Okay, and do you have a link to this paper? Is this a Zyphra paper, or is this a?
Yeah, yeah, I do. Where should I send it? I have links for all of this, so.
Yeah, let's get back to that because yeah, we could find that. What's the name of the paper?
It is this paper. If people want to, the case for co-designing model architectures with hardware is the sizing one.
Nice.
And then the Zyphra one is Zyphra AMD. So this is the blog that I keep referring to. We were able to beat NVIDIA H100 for flash attention too. And this goes into a little bit of high level detail of how we did that.
Gotcha. One of the things I notice every year when I go to like GTC is I learn some new magic number that I didn't know about, right? that comes about with the new hardware that's completely or relatively undocumented. Of course, depends often on the workload and the type of model and all that stuff. Like, does NVIDIA, and I guess same with like AMD, like, do they work with these model like creators for the popular models? Do they work with Meta and to optimize these things and say, hey, make it a multiple of 64 or whatever?
More so now, but things still fall through the cracks, I would say. The way I would have envisioned this is Meta would have like a dedicated team from NVIDIA supporting them, and they would say, hey, we're getting lower throughput, and then it would just sort of be a back and forth from there on diagnosing where that's coming from. And whether they find the sizing is kind of up to them, and whether Meta wants to change the sizing. Ideally, Meta would have within Meta itself would have like a model side that would say, okay, we want 1,023 neurons we find is the best accuracy, and then they would have like a hardware team there that would say, okay, let's round it up to 1024 and give slightly better perf, and you do it within the organization. That would be guaranteed to catch.
Got it. And I can see in the GPT-3 days, because it was so early, maybe it wasn't on NVIDIA's radar. But the second those things start like getting popular, yeah, I feel like they should have people, reaching out and saying, hey, change this right now. This will, help you out. So,
but it happened for a long time. So I listed a lot of models there that were trained with a GPT. So those maybe like a few years there.
That was a couple years, huh?
Yes.
Oh, right. Yeah. The co-design stuff. OpenAI actually gave a webinar a few weeks ago. I saw where they had their systems folks in there talking about co-design. So that's becoming kind of a popular term these days.
Yeah.
Knowing the hardware and then kind of working back and forth.
Yeah.
So
because they've had to infer them at scale. So like they've had to infer GPT-4 at scale. They know exactly, okay, these are the things I would have changed when I was training to make it easier for me during inference. And then they have their own like internal loop of, okay, the next one is trained to be easier to infer and so on. But go ahead.
Got it. Yeah. Good. Okay, cool. Yeah, that's right. That's a good point. During inference, they realize, okay, yeah.
And we're at Zyphra, we're trying to do that, but for all kinds of hardware. That's why it's so hard and why I spend so much time on it. Is because I'm going to be, in 6 months trying to get this running on a Samsung phone, and I don't want to hate myself. I want to like make the model amenable to all of those different GPUs now while I'm training it, that sort of thing.
But then don't you have the kind of least common denominator issue where maybe it works well for many, but it doesn't work the best on
So we
specific.
want to make that exact decision at training time. So if we want to make it good on AMD and MI300X, NVIDIA H100, and Samsung, but then that would make it bad on iPhone, I need to know that when I'm training. Ideally, I make it good for everything, but I need to at least know which hardwares I'm leaving out at training time. In the worst case, I want to at least know and then account for that later on.
And account for it later, right? When you switch to a new device, or add support for a new device, or Vera Rubin's going to come out sometime next year. Are you
Mhm.
do you have to go through this entire process?
Yeah, unforeseen hardware is always a pain. On the plus side, like ever since a lot of these boil down to how well do you use the tensor cores or matrix cores or the neural engine or whatever else on an iPhone. How well do you use those subunits on your SIMD system? And these were introduced in Volta, which is a very old GPU for NVIDIA,
Mhm.
and NVIDIA does a good job of making this backwards compatible and actually loosening the constraints of how well you can use your tensor cores. So remember, like this slide, for example, let me go back. This one. So this was on A100s and V100s. On H100s, there's less spikiness going on because they make tensor cores more usable by more data types, by more sizes. They make like they won't be able to solve every edge case, but they generally make it easier to use those tensor cores because those tensor cores are how they show the 2x speed up every generation. They do more and more in the tensor cores.
Right.
And then AMD is in the position where they want they want the models that you've already trained, since they're sort of catching up on NVIDIA, to also work well on AMD. So their matrix cores very closely approximate tensor cores. So that makes that sort of problem easier, and then other hardware vendors try to follow suit. So it is a problem that's hard, but it's not insurmountable. A lot of hardware tries to converge to the same tensor core sort of look.
Got it. And yeah, I mean, that's kind of a pitfall, is if you are somehow not using those tensor cores and falling back to the FP32 cores,
That is what these are here.
Yeah,
Just
yeah.
even if it's in the same data type. If you're using CUDA cores, then you have much worse performance because they're not highly optimized for those matrix multiplications.
Got it. We have a question here from Michael. Any gotchas for quantization between NVIDIA and the AMD?
Yeah, that one's still kind of an open problem we're trying to fix. I would say FP8 on AMD is like almost being added on the fly. So after they released the hardware with FP8 and software wasn't available until like just a few months ago. At least available in a usable sense. So that's always a gotcha. I would say FP8 for like Flash Attention 3 and that sort of thing. Like it's totally unusable on AMD, and this kind of thing needs to be accounted for. So for those specific two, yeah, AMD is a bit not as advertised for FP8 specifically. You need to account for that.
Interesting. One of the questions I had typed in earlier for you was, which is just to remind myself because they were coming up as I was going, but if there was one or two things from each of the NVIDIA and like AMD communities that you would want, what would it be?
In what sense? You said from what communities?
From just like the NVIDIA, folks and the AMD folks, right? And so, for example, FP8 stuff from AMD, right? Like figuring that out, getting that out there sooner and into the software. I mean, are there other things like that have frustrated you?
I mean, yeah, definitely support what your hardware gives and what you promised. That one's for sure. But in general, I would say AMD, really, they've caught up more than people realize. And I think they just need people to write tutorials, and this is how you run your Hugging Face model well, that sort of thing, to make it more approachable so that it's less scary to run an AMD. Hardware was already figured out with AMD MI300X. It's much better than their earlier GPUs, and software has also improved a lot. Just tell people that composable kernel is out there. Tell people that you can run your models with flash attention on AMD, and it works well. So for them, to be honest, I just want dissemination.
Yeah.
As a developer, AMD's developer docs are lacking, but that's just, I think there's just not a huge army of developers all the time writing stuff. So I'm trying to be the difference here. Yeah, honestly, communication, documentation, that kind of thing. I've had to sift through so many AMD like low level user guides trying to figure out what the problem is when instead I hope people have nice blogs and stuff.
Yeah, that's the thing, when I'm out there Googling for something with NVIDIA, like the PTX instruction that I'm trying to track down, there's there's not a lot, but
Hmm.
like there's enough that I can make it
Yeah,
through. And I'm curious because it doesn't sound like that's the case for
yeah.
like AMD as much.
I almost have like brothers in arms, right? I try and find other
Mhm,
companies trying to work on AMD, and I'm like, okay, FP8's not working for me. Like,
mhm.
am I crazy? And then like we compare notes, and that's the reality. But if people don't, aren't in the Bay and talking to these people, then it's much harder to do this. So they need to disseminate.
Yeah. And I was actually surprised. I had just heard recently about right, like XAI using AMD
Hmm.
for like inference, and I guess it kind of makes sense because they are very much behind SG-Lang project, which
Yep.
has like pretty good support for like AMD. Um, do you know if so on the VLLM side, I think there's like AMD support for that project, but
There is. And it's pretty
is
good.
that okay? Is it? Yeah.
I would say so. Yeah. Um, there's still like you kind of need to know which container works well. Like their
Yeah.
containers are just kind of dumped out. They don't say this Docker container has this changes from these sort of things. So you're gonna have to play around yourself or know someone who has worked with VLM and AMD. But once you get it set up, then yeah, VLM is very competitive on AMD, and we use it.
Oh, gotcha. Okay. Is it the community that's contributing, or is it the like AMD folks themselves contributing to the VLLM?
Right now, the AMD people are a higher proportion to the community compared to like NVIDIA, so they're often the bottleneck. And I don't envy the position that they're in, but they have to be the ones pushing it themselves, and they're man-hour bound.
Yeah. Interesting tidbit. Speaking of, technical marketing for like AMD, they just lost their like director of
Hmm.
technical marketing, went to NVIDIA.
Yeah.
So,
I
so
will
that's
do it
not
for
good.
them though. I will shout from the rooftops that AMD is good. You just need to try it. And if you're a large organization like XAI or whatever else, then it's definitely worth the man hours to
Yeah.
figure it out.
Interesting. Okay. And oh crap. Yeah, I actually yeah, I have to jump for yeah, for my
Okay,
10:30. Hey Quentin, man, thanks so much. Yeah, this has been awesome. We'll post this to YouTube. And yeah, hopefully we can have you on many more times. So
cool. We'll love it. Thanks, Chris.
all right, everyone. Thank you.
Bye.